Hello, everybody, and welcome to this week's... Okay, someone is still echoing. Hello, everybody, and welcome to this week's Deep Astronomy Hangout. My name is Tony Darnell. I work at deepastronomy.space, and today we do this every Thursday where we get together and either we discuss the future in space travel or space exploration, going to Mars, the ISS, what are our efforts to getting human beings up into space, and on alternate Thursdays we have the Astro Coffee Hangout where we talk about the latest discoveries in astronomy from professional astronomers. And so these are, and Harley will tell you just a little bit more about this in a bit, but these hangouts are co-sponsored by the American Astronomical Society and the American Astronautical Society, both of whom put on different aspects. And this one, the Future in Space Hangout, is done by the American Astronomical Society, so I want to thank them for their support. They provide this as a service to their members to get the word out about astronautical things of interest. And so today, after this July 4th holiday, we're all done looking up, as we often do on the Deep Astronomy, but while we usually look up at the stars and the planets, yesterday we were looking up, at least in the United States, at fireworks. We're done with that, and now we're going to talk about going to Mars. And this particular topic, we will be discussing how are we going to afford it? What efforts are being made to afford such a huge endeavor? It is expensive, as I'm sure you can all imagine. And so my guests today are going to have been doing some work along those lines. They're going to tell us what they're coming up with, building, hopefully constructing an architecture that lets us afford going to Mars, doing some cool stuff, and getting back safely again. So let me pull up my co-host, Dr. Harley Thronson. Hi, Dr. Harley.
Hello, good afternoon.
It's good to see you, and you put these together for us every other week. So you want to give a brief intro to the Hangout and sort of what the spirit of these guys are?
Sure. And again, thank you, as you've already done, to the American Astronautical Society, which sponsors this, in order to inform interested listeners about some of the latest work, the latest results in human and robotic exploration of the cosmos. Sounds great, and it is. All right, the background to this is that for decades, at least since the 1950s in a serious way, NASA, partner agencies elsewhere, academia, industry, have been examining, debating, discussing how to send humans to Mars. And no doubt about it, it's going to be an expensive endeavor. And there is a mythology around which we are going to break during this discussion, that it is unaffordably expensive, unambiguously expensive, but not unaffordably expensive. And we've got two individuals who have been leading teams, been part of teams in developing scenarios and architectures and costing scenarios and architectures to send humans to Mars, Joe and John, and let's introduce them.
Okay, will do. Okay, before I do that, let me just real quickly mention we want you to interact with our guests and with us, and you can do that by obviously the live chat on YouTube, as well as our Discord server. The link to the Discord server is in the description box, so please interact with us in each of those two ways. I already see a lot of you guys there. Christian Reddy, well, I haven't seen you in a while. Cheers, guys. Yeah, first time on one of these Hangouts. Well, welcome. Also, Peter Q is there, John, Galaxia, lots of people are here. So welcome, everybody. Please ask our guest questions, but you need to know first who they are. So let me start. I'm just going on my little screen here from left to right. First up is John Connolly. He works at NASA's Johnson Space Center. Hi, John. You want to give a little brief introduction into who you are and what you're doing with in respect to our topic today.
All right, thanks, Tony. Well, I head up NASA's Human Mars Study Team. We're not an official program, so all you can be is a study before you're a program. So right now, NASA has a team looking at what the best way is to get humans to Mars, what the options are. And whenever one of these exercises come up to see how we can make it more affordable, we certainly participate in those exercises. So my team is basically always on the lookout for new technologies, new techniques for getting folks to Mars, also making sure that the stuff we're doing here in the near term, like Gateway, is focused at getting us there. It's not taking any wrong turns. And And so what we're going to talk about today is a little bit of work we did on affordability and in general why Mars is hard, but maybe not impossible.
Yeah, okay. And by the way, let me just add that I'm really jelly of that model in the background. That looks really cool. Okay. Also with me is Joe Cassady. He is from Aerojet Rocketdyne. We've seen both of these guys have been on Hangouts before, but the last time Joe was on, we were talking about electric propulsion techniques for getting like trucks, cargo to Mars and things like that. So welcome back, Joe. Maybe give us a brief intro into who you are and what you're doing in respect to today's topic.
Oh, thanks. Yeah,
you're there.
Yep, I just got that cleared mute there. Thanks, Tony. As you said, I work in Aerojet Rocketdyne, actually here in the Washington office. And one of the things about the stuff that John was talking about that we do, and I should say I also am part of a group called Explore Mars, where I serve on the board. And one of the things we try to do is look at the intersection of policy, which is why it's helpful to be in Washington, and engineering, technologies, as John mentioned, and public outreach. And so as we've been looking at these things and trying to break the problem up a little bit so that we can better quantify it, that's something that we then communicate out and try to, as Harley alluded to earlier, we started off a few years back, there was a myth out there that said it would take $1 trillion to send humans to Mars and get them back. And everybody just sort of bought into that without questioning it. One of the things we always looked at was this $1 trillion boogeyman, and I think we've effectively beat that down now. So it's something now I think we have a better quantification for. We know what the hard problems are. Some of those we don't have solutions for yet, but we have plans for how to break it down and reduce the risk, and we can put dollar figures against those. And then really what we need is we need to show that the rate at which we spend those dollars does not exceed something like the International Space Station that we just did over the last 30 some years, and that's within the the range of dollar expenditures that we're already comfortable with, so that we can set ourselves forth to go forward on the path to get humans to Mars and back. I always like to say that because when I talk to people and casually over the holiday weekend and things like that, and people ask me about this, they always say, "Oh, but you're not going to be able to bring them back, right?" No. We're going to bring the people back.
Okay, well let me do this real quick. Let me pull everybody up. Okay, well let's start with that, Joe or John. Let's talk about. I want to go back to this rate of spending that you just mentioned with the ISS, Joe. But tell me, so we heard this sort of mythical $1 trillion to get us there. How much do you guys think it is going to cost realistically? And what kind of mission is it? Because we're talking about there's like different ways of going to Mars, right? There are ways we could just do a moonshot kind of thing where we go, we spend a few weeks there and we come back. Then there's the ones where we have a much longer term presence on Mars. So I guess I should ask that question first. What kind of mission are you trying to cost? And then how much?
Hey, John could give you a good overview of our last workshop. That's a really great segue into that.
All right. All right, John.
Okay, so let's start at the beginning. When you're asking about how much does a mission to Mars cost, the logical question is, well, what kind of mission? So the kind of mission that has people going permanently and leading towards permanent human colonization of Mars? Is it more of a sortie class mission like we did in Apollo, where you're going to different sites for short stays and coming right home? Or is it something in the middle? And each of those has a different cost and a different cost curve that goes with it. And so the last workshop we did back in December, which was called Affording Mars 5, fifth in the series, looked actually at all three of those. And we were interested in exactly that question. What is the cost difference between a kind of a quick sortie type mission, an Apollo class mission, if you will, but certainly much more than Apollo because we're out at Mars and the physics dictates you're going to be there for a while. Kind of an intermediate mission, which was what we term a science, sort of a science research-based type mission where you're going and you're setting up some infrastructure, much like they did in the early Antarctic expeditions, and which is still going on today. So you have field camps that you're going back and forth to with subsequent crews. And then the one on the far right was a mission that was leading to eventual human habitation of the planet, permanent habitation. And there's obviously a sequence of events where you could start with one and go to the next and the next. But we were kind of interested in what the cost curves were for all three. And so there, I set up the missions. Now I'm going to actually hand the difficult answer over to Joe.
And if you want me to put up any of these slides you have, just say the word.
Mm-hmm.
Yeah, if you've got the one from the FIFO handout that shows the sand chart, you know what the sand chart is, Tony?
I'm afraid I don't. Is it?
Oh, it's the one with sort of the different color regions that stack up to make the total. I don't know if we had that one. I think we had that one in there. I'll talk about it anyway.
Oh, the AMV Group 1 cost estimate?
Yeah, that's Group 1. That's fine. I'll explain. Group 1 is basically what John referred to as sort of the Apollo sortie style, with the big difference that, yeah, because we're going to Mars, the physics of going to Mars means you're still going to be out there a while. The sortie part is how long are you on the surface? And so I think in our case, I was part of Group 1. We were looking at a few weeks on the surface, and the rest of the time, while you're waiting for your window to open up to come home, you're in orbit, basically. But you do get people to the surface of Mars, and you do have the opportunity to bring back samples and things like that are kind of the important pieces of why we want to go and do some of the first human flights to Mars. So if you pull that one up, I don't know if it's...
Which one is it again?
Oh, the cost summary.
Cost summary. All right, hang on just a sec here. Let me.
And what you would see, as I'll start to describe it while you're looking, is that we set ourselves a goal that the expenditures would not exceed the current rate of expenditures that NASA has for human spaceflight operations, with the addition of, I think it was, correct me if I'm wrong on this one, John, I think it was 2% or 2.5% inflation annual rate.
Yeah,
So we gave ourselves that
inflation rate. Yes.
Yeah, just basically put on a nominal inflation rate, and so we drew a line that showed that dollar limit, and our challenge was to try to stay under that limit over the intervening time between 2018 now and 2033. The best opportunity for one of these missions in terms of the alignment between Earth and Mars and minimizing the delta V requirements is 2033. There are other, every 2 years, other opportunities. So we sort of set a target of 2033. If not that, then 2035, 2037 are sort of the next couple opportunities. But what we came up with was an answer that said, looks like we could do that. We could actually stay under that limit.
Okay, I'm not seeing
fact,
Joe, I'm trying to find the slide, and I don't see anything that says a summary on here.
It's slide 11 in that FIFO deck.
Thank you. That's perfect. Okay. Well, that's what I just had up. Oh, okay. Well, there we go. There we are. It's up. Can you see it, Joe?
I can't, actually. I'm still seeing John.
Oh, well, it should be there.
And that really nice Saturn V model.
All right. Well, just if you know the slide, it's just trust that it's up.
Yeah, sure.
So go ahead.
So hopefully the viewers and the listeners can see it out there. But basically, you see, I think the line that shows the limit that we were trying to stay under, and the individual colored pieces are elements of the development that have to happen. And there was another assumption that we should talk about, it's kind of pertinent to the discussion, and that was that we would see the expenditures on the International Space Station drop off, and we would be able to take advantage of that wedge of funding to devote to this. And so that's kind of consistent with the discussion that's going on out there right now about how long do we keep space station active. And in reality, it's not that we're going to deorbit space station necessarily, but just that we're looking at ways to take the space station and find other ways to use it as sort of a commercial platform, or elements of it as a commercial platform, so that NASA isn't solely responsible for footing the bill for the space station.
Okay, so the y-axis
somewhere in the 20. I'm sorry. Go ahead.
I'm just saying the y-axis here is in billions of dollars.
No.
It says Mars supplement cost.
Oh, I'm sorry. Yes. There it is. Yes, I can see it now. Yeah, that's right. Billions of dollars. So typically, you're looking at somewhere in the $3.5 to $4 billion a year range now, and we're as I said, the budget that we're using for this over the roughly 20 years is adjusted for inflation, and that's that dash line that you see with the ISS equivalent budget description.
Okay, so I just want to make sure I'm understanding. So we've got this linear increase in ISS spending going from about the lower 2020s up through 2045, and you're projecting it to be more or less linear with a slope that's not very steep. You're looking going from about 4 billion to roughly 7, but all this Mars stuff is underneath that, and it's going up and down. Where with I guess when things are being built and when things are being launched and things like that. But it needs to stay underneath. You're saying, and you said this at the beginning. It needs to stay underneath the spending that we've done for the ISS. Is that a goal that you've just?
That was a goal that we set for ourselves because we were trying to bust this myth of unaffordability, and our assumption, our sort of going in position was, if we are willing to commit to a long-term program similar to the space station, and if the budget per year is not, that much more than that was, or equivalent in terms of that, it was 2.6% inflation, now that I can see the chart, then we believe that that's not something that people would balk at, people being both the public as well as the congressional stakeholders. And we have had a lot of support for that. So what this shows is it is quite possible to do that, and to have a Mars landing in the 2030s, and then a series of those leading up to what we call a long stay landing. So again, this was group one. This was more of a sortie approach at first, but building the capability toward where we could stay longer, and sort of go into what John referred to as the outpost type missions, where we send people to the surface for hundreds of days.
Yeah, let me note one thing. Joe, note one thing here, that these series of AMs, achievable and affording Mars, for the interested folks in the audience, these series of reports and presentations are available on the Explore Mars Incorporated website. Folks can use their browser to search for Explore Mars Incorporated and look under their drop-down under projects, and you will see, you can pull up your choice, whichever one of the AM workshops you want. And this one will shortly go up, so folks can look at the numbers themselves and debate among ourselves or themselves the assumptions and the results of this activity.
Okay, now let me go back. I'm sorry, before I go back. So you guys have according to this, you're estimating the first Mars landing, and this is against a Group 1 type mission, which is, what was it again? What's a Group 1 mission?
So it's similar to like an Apollo style sortie, but again, going back to what John said, you're still out there for 1,000 days. I mean, it's about a 7-month transfer out. You're in the Mars vicinity for a period of like several 400 days, let's say, and then it's 7 months back. So the total time you're out there is going to be around 1,000 days. Your time on the surface is limited, and that actually helps us in a lot of ways because of the capacity for the landers that we have to go down. If it's just a few weeks on the surface, obviously you don't have to take as much stuff down to the surface to support the crews. And that was the ground rule that we went in with on this group, was to limit that. But I'll say this: the other two groups looked at the mission that John referred to as Outpost as well as the final group looked at sort of human colonization approaches. And what you see is the rate of expenditure doesn't necessarily change dramatically. The time scale is longer before you can actually, and so, you know, if you look at these sort of as a rubber band type approach, this gets us there faster. We can't do as much on those early missions in terms of time on the surface, but it gets that, you know, if we want to have an achievement, say we're going to be able to do it, and we do knock down things like EDL, entry, descent, and landing. Some of the tall poles get knocked down even on these sortie missions.
Okay, so please correct me if I say this wrong, but the big takeaway from this graph is that we can get to Mars. We could do a crewed moon landing test. We can do a Mars orbit mission test. We can do 1, 2, 3 landings on Mars through 2045 and stay underneath the budget that we currently spend, adjusted for inflation, on the International Space Station. We can do it. That's the takeaway from this.
Notice in the early 2030s, we're well below that line. So there's actually room to support some additional technology development or potentially even add some capability to those missions in that area that you see as sort of the valley between 2030 and 2035.
Okay. All right, guys, I just want to have to ask this. I'm in a bit of a mood, and we all are, because we just got through learning about the cost of the James Webb Space Telescope mission, and it's going to be really, really, really expensive and really, really, really delayed. So how confident are you of these cost estimates, and how can you even possibly know what some of this stuff is going to cost? I mean, I'm sure that by now in the mid-2020s and even the 2030s, when NASA wants to get to Mars, boy, the climate, the cost of things. I mean, what do you guys talk about in these meetings about how confident you are in these cost estimates?
All right. Well, I'll take that first. So first of all, cost estimating is somewhat a black art, especially when you're trying to estimate the cost of something you've never, ever done before. I'd love to see the initial cost estimates for the Apollo missions, for example. So I think we can do better than that today, because we do have experience with human spaceflight. But it's true, we've never built a Mars lander. We've never built a interplanetary spacecraft before. So our cost estimates are based on things we know how to build, extrapolated out for what we think the extensions of technology and things like that are. So you know, unfortunately, I don't think the confidence is very high, but it's the best we can do right now. When you're trying to build the first thing ever of a certain item, like the James Webb Space Telescope, it's very hard to estimate the cost of it, because you literally have nothing to go by. And so, so you're exactly right that the cost estimates we have are they're very good for comparing one architecture to another architecture, because they're all costed out the same way. But as far as the absolute value goes, you know, you have to accept the fact that there's a lot of uncertainty in there, just because this is all new stuff.
Okay.
Yeah.
Go ahead, Joe.
Tony, let me just say that I agree with John in one sense. On the other hand, one of the things that we are trying to do, especially Group 1, we didn't use a lot of new technology. You know, we had the other hangout where we talked a lot about new propulsion technology.
That's right.
And we didn't get as exotic as some of those new propulsion technologies that are out there. We used pretty much all standard stuff, except for the cargo. We did use a solar electric tug to get some of the cargo out, but it wasn't a really high-powered system. So we're kind of looking at starting with things that we do build today and extrapolating only so far, and that helps a little. Everything John said is right. It's just we're trying to be a little bit careful not to say, yeah, we can get a multi-megawatt nuclear electric propulsion system, and you know, the crew goes with the cargo and it looks like the thing in the Martian. It's not going to be like that.
Okay. All right. Let's talk a little bit about, since one of the things is affordability and our spending on the International Space Station, keyword on international in this one. We're not looking, you guys aren't looking at doing this by ourselves. We're not looking at NASA and Aerojet Rocketdyne or the United States doing this on our own, right? Can you talk about the international component of what you're planning? Who else wants to go to Mars?
Well, a lot of folks do, it turns out. A lot of folks want to go back to the moon too, also. So there is a logical progression that starts with the partners on the ISS, then goes through the moon and onto Mars. And I think you're right that there's no way that a mission to Mars will be done, by one country like we did the Apollo program. I think making the Mars program kind of equivalent to the ISS, the way it was shown on the cost chart, is really good, because not only does it sort of show that we could do a mission like this with about the same resources we spend on ISS, but it also gives you an idea that to do that, you need the same kind of international commitment, or maybe even greater international commitment that we had for ISS. And so international partnership is going to be one of the huge pieces of making this affordable. There's other pieces too. Getting the commercial space folks involved. That's new, and that's something that's very exciting. Also, going with reusable vehicles. That's something new to NASA, and SpaceX is proving that they can do that pretty well. And then I think there is another element about testing stuff on the moon in getting ready to go to Mars that will drive maybe cost a little bit, but will certainly drive risk down.
Okay. Now, you may have mentioned this while I was searching through the PowerPoint slides, but I want to know: are you planning on using the Space Launch System, or some? You mentioned reusable rockets just now. Are we looking at maybe using one of these companies' reusable rockets to get us there? What's the backbone that you're planning on?
It's a mix, really. We looked at, I'm again speaking for Group 1, but I think it was true, John, and the other two groups too. We had SLS as kind of the backbone, but we also had frequent opportunities for commercial launches to support. And you flashed up the one thing we call a bat chart a while ago, Tony, that showed a lot of subway map-like connectors with launch vehicles on Earth and things going into intermediate orbits. And when you look at that, if you look at that graph or that chart again, you see on the bottom several SLS launches. I think in Group 1, if I remember right, we had about 5 SLS launches and about 5 commercial launches. So it was almost a 50-50 mix.
I see.
All right. So if you show slide 17 from the FIFO deck, Tony, that shows the bat chart that Joe was alluding to. And if you notice, that shows a combination of commercial vehicles and NASA SLS launches. And I think that's pretty accurate, that it's going to take a combination. A Mars mission just requires a lot of mass delivered to orbit to get started. I mean, and most of that mass is fuel. And so there's really, really good opportunities for commercial delivery of piece parts and fuel and things like that. So I think it's going to take a mixed fleet to get us there.
Okay. Here, I'm sorry it took me a while, but my computer is
there you go.
My computer is
is
at its peak. Yeah. So all right. Well, you got to explain this, because it's a lot going on here.
Okay. So a bat chart is a classic NASA way of showing a mission profile. You have the Earth on the bottom, you have your target planet on top. As you launch things from Earth towards the target planet, they kind of hang off the target upside down like bats. So thus the name bat chart. But if you look across the bottom, you start out with all the Earth launches. And if you notice on this particular chart, they've lined up a Blue Origin launcher, a SpaceX launcher, and I can't tell what the other one is exactly. Another commercial launcher, probably one of Joe's. And the idea there is that these are opportunities for commercial vendors to provide launch services for these missions. And then you can see there's a couple where you need some very big payloads, like NTP stages. And
I'm trying to zoom it up for you here.
yeah, thanks.
And move along. So I mean,
And show some of the big pieces might need the biggest launch vehicle we have, and if that happens to be SLS at the time, then that's what we'll use. But if you notice, it's not exclusively SLS launches. It's not exclusively commercial launches. It's the whole fleet.
Yeah. Okay. All right. Let me just zoom this back down a little bit.
Yeah, I think one of the principles that we kind of are, tripping to is we need the best of what everybody has out there to do something like this, and that includes the international partners. Some of them are very good at certain elements of this too, and we're really finding that there's a nice way to bring all these things together. And don't reinvent the wheel. There's just not enough time and money to reinvent the wheel. You got to take advantage of things that people know how to do best. And John said it well. Some of the new commercial folks coming online are showing the ability to do reusable and other things like that. Definitely want to take advantage of that too.
Okay. Yeah. All right. All right. Well, so the I'm just looking at some of the questions here. I want to get to some of them here in just a minute, but okay. Well, I asked you about your confidence level. I asked you about the international capabilities or the international interest, and you said there was quite a bit. The thing I've noticed about NASA, and I know they seem to have to do everything with this. Well, whatever the political winds are, we're going to need to be agile enough to ride that wave, right? So right now it's all about the moon. It was about Mars, but now it's about the moon. We got to get to the moon. We got to have cislunar stuff. And so everything, but NASA goes, okay, well, you know what? It's not a big deal because all the stuff we did to go to Mars also gets to the moon. At some point, you have to say, well, we're going to Mars or the moon, and this is our plan. Now, your first chart that I showed you did have some moon stuff in it. Is that working into your cost of going to Mars, or is that just a separate thing now because it's going to the moon, it's not going to Mars?
Well, Joe, that was a Group 1 chart, so why don't you explain?
Yeah, sure. Tony, it's interesting. Before it was all about the moon, we were already still talking about something that in those days we referred to as the proving ground. And if you look back, and I could send you the charts from 5 or 6 years ago, we were talking about sending things out into cislunar space because I mentioned earlier, you're going to be on a 1,000-day journey. There's no way to turn around and stop and come back if something breaks on your way to Mars. So you want to check all those systems out first and really make sure that those systems, especially the ones that involve crew, are well wrung out before you jump off on that big jump out to Mars. And so really it is on the pathway to Mars, and it always has been. There's been a little shift in the emphasis, but I think the way I would say it is now, what we can do at the moon in terms of the infrastructure there will help support other people who want to do things relative to the moon, like commercial folks who want to go do resources on the moon or whatever. We'll support that through the infrastructure we build up, but at the same time, that infrastructure helps us wring out the things that we need to wring out and get working before we make the jump to Mars. And that could include things like going, down with a lander that we want to use on Mars. We're actually going to do a workshop coming up here. Now's the plug. This is the part of the show where we do the plug. We're going to have Explore Mars, and AES are going to put another workshop on at the end of August timeframe, where we're going to look at how can we best use the moon to go to Mars, and what are the things that we can do on the moon that will support going to Mars. And I think that's really been something we've thought about doing for quite a while, not just the fad of the hour.
Okay.
Yeah. So if I could add to that, Tony, if you look at an overall exploration architecture that somebody like NASA might advocate, you could go directly from the Earth to Mars and not do anything at the moon. My opinion, that would be a very high-risk mission. and maybe you accept that risk, maybe you don't. If you want to buy down the risk a little bit, there are things you could do on the moon to test systems, to test pieces of hardware, to test operations that will make the Mars mission a lot less riskier. And so, like Joe said, that we're actually holding a workshop to answer that very question. What are the logical things you could do on the moon to get you to Mars? Now, there's a lot of illogical things you could do on the moon that don't get you to Mars. And, some of those may be valuable as well. But since we're talking about Mars, we're talking about the subset of all the things you could do on the moon that are, no kidding, the most applicable things you could do there that have real value to getting to Mars. So I think there is a logical place for the moon on the path for Mars, just like there was a logic in doing Mercury and Gemini before Apollo.
Yeah, I can imagine things like ISRU or in situ resource utilization experiments on the moon would be handy to then go to Mars. That'd be something I'd like to see done anyway. But okay, well, in your cost estimate, when you are, by the way, I got to laugh at Andrew Planet's question. He's asking, why don't we send much smaller I'm sorry. Why don't we send much smaller astronauts to Mars using technology that is also reduced in size, so save costs all around? Just send little guys, little astronauts out there. You guys actually looked at that? Is that what you said, Joe?
Yeah, I was just kidding. But it was like Funny I Shrunk the Kids, right?
Right. Yeah, that's funny, Andrew. No,
but I suppose there is some logic to that. I mean,
the Apollo astronauts were actually, they had height requirements. They couldn't be taller than like 5 foot
right.
something.
Right. They were about no bigger than the 50th percentile American male, and the current astronaut class typically ranges from the 5th percentile female to the 95th percentile male. So to be inclusive of people of stature, we've actually expanded.
Sizest, man.
We've expanded, how big and how small astronauts can be. Sure, if it's smaller, people consume less food, less oxygen, and all that. So there is some.
And everybody knows they have bigger tempers, though.
But that's not in our current plans.
Okay. Well, okay. So back to the cost estimate. Thank you, Andrew. That was a good question. The role of private companies. Obviously, they're taking a lot. I mean, President Trump wants to contract out a lot of the ISS stuff as soon as possible to private companies. NASA is looking into doing that. When you figure out what something costs, I'd like to know what role private companies play in this. And do you just use them as contractors? You just say, okay, SpaceX, we need you to do a launch to the moon for, what's your bid? Is that how you do it? Or do you think that maybe they can take it on as some kind of profit-making thing and just hand the costs off to them? I mean, I just wonder what role private companies play in this. Is it just contractors, or they do have a more integrated role?
Yeah, I'll just throw out one example. I think that, John, this is a good one maybe. I mentioned entry, descent, and landing earlier. In something like that's something we've never done before, we've done it up to a certain level with our rovers that we have on Mars now, but that's about 1 metric ton. And we have to land about 20 metric tons to support human scale expedition, human landers. So it's a big jump, and we know we can't do it the same way we're doing it now. So things come into play like supersonic retropropulsion. And I like that example because right now, what does SpaceX do when they bring the boosters back? Well, they're doing supersonic retropropulsion. And they've done a lot of the NRE work, the non-recurring engineering. They're getting data that believe John is true, they're sharing with NASA. And NASA doesn't have to do that. NASA doesn't have to pay for that. NASA can take advantage of that data. I mean, they may have to pay a little something, but it's not like they're the only ones looking at that and funding it. So you're taking advantage of the company's own interest that they have for doing something completely different, but you're applying it to the problem that you're trying to work, which is, and it turns out that high up in Earth's atmosphere where they're doing a lot of that, it's a good analog for Mars. So you don't have to go to Mars to test this stuff out. You can do it up in the high, less dense parts of Earth's atmosphere. So that's one example of how you can use a private company to accomplish something that you want to do. And you can also buy services from them. That's true too.
Yeah.
Right. So it comes in many flavors. We have commercial companies out there doing individual technologies like supersonic retropropulsion that certainly benefit what we want to do to land on Mars. And maybe more importantly, we have companies out there developing entire capabilities, space launch capabilities that used to be done by the government, and now we could simply buy those services from private companies. And we're currently working on for example, lunar lander delivery services. That's a huge next step. Not to quote someone famous, but a giant leap.
Yeah.
When you think about it, we will have companies here in the U.S. who will have the capability to land things on the moon for us. That's a capability that only a couple nations in the world have right now. And that's pretty outstanding, actually, that we have that kind of commercial base. And it's kind of exciting because that actually frees NASA up from being a kind of an operations company, and processing through lots of hardware to actually spending money on the stuff way on the far edge of exploration. So I'm very excited about what's happening in the commercial world because, that's the role of government is to seed those kind of companies, and when they succeed, to get out of the way and purchase services from them.
Okay, I'm going to ask one Plot's question, and then I'm going to slightly rephrase it into a related but different, a little bit different. He's asking, what are you looking at when it comes to human costs, radiation protection, psychology, muscle waste, training? How will this impact costs for preparing astronauts? And I guess I'd like to reword that just a little bit to say, when you're doing this cost analysis, you break things up into different categories. Of what into certain percentage, like launching things costs this much of a percentage of getting us to Mars. Habitats cost us another X percentage of getting us to Mars. What percentage of the human protection scheme goes into the cost of a mission?
Well,
is it a big one? Is it a little one?
No, it's surprisingly small.
Is it?
Because of the physics of moving around in space, propulsion is always the dominant cost.
That's the biggest. Okay.
All of the systems that it takes to keep the crew happy and healthy all fall under a category called human health and performance. And mass-wise and cost-wise, that's actually kind of a tiny sliver of the whole cost pie. It's important.
It's a little surprising, though. You would think that things like human subsystems, breathing, environment, atmosphere, food, waste, that'd be quite a big part, but it's not, you're saying.
Well, ECLS, when you get into environmental control, ECLS, yeah, that
if you include that, okay, I was just asking about the safety part, so yeah.
Right.
Okay.
But then all the other things like radiation protection and exercise equipment and medical equipment and food and all those other things, in terms of the big picture, the big cost pie, those are actually, a very small sliver of the whole thing. Very important, of course, and we got to do it right. But when you're talking about moving around in interplanetary space, and everything you're talking about is in units of kilometers per second of velocity change for one maneuver or another, propulsion, cost of propulsion is going to dominate the cost world.
Okay. To what extent do? I'm sorry. Did you want to comment, Joe?
Oh, I was gonna throw in another little kind of add-on to that, which is, getting back to what we said earlier, we're not going to do the big nuclear electric spaceship like in The Martian, but we're also not going to have artificial gravity like they did either. So, there are things we're not spinning up the spaceships or anything like that. That could come later. What we're doing is we're setting up for the.
Well, you're trying to get there on the cheap.
The crewed vessels for the Lewis and Clark expedition. We just want to get out there and see what's out there, and then later on, people will figure out how to build the real fancy ways to go in comfort style.
Guy, can you imagine what it would be like that mission? 1,000 days, and it's going to be uncomfortable, long, and you're trying to do this in a cost-effective way. It's, it'd be nice to have some artificial gravity, but no, you got to go without. So that brings me to contingencies. When you plan on the cost of something, do you take, what sort of contingencies do you think about? Let's say, gosh, we don't want them to get stuck on Mars, so we have to build X number of fail-safes and backup systems such that they are sure to get off of Mars. How does that go into the thinking, and where is that in the budget? Is it in the return phase, or is it just throughout the whole mission?
Okay, I'll go first, and then Joe could fill in. Every time we do a spacecraft design, there's a certain amount of redundancy assumed in the design. When you get to certain systems, the amount of redundant systems or dissimilar redundancy that will take the place of that systems increases. But so there's built-in redundant systems to all these estimates that we do. Now, that's kind of on the piece part level. When you start talking about big things like maybe a failed launch, let's say that you have a launch vehicle on the pad and you're launching a lander that's going to Mars, and something happens and that lander doesn't make it to orbit. Do you have contingencies in your cost estimate to handle a failed launch attempt? And typically we don't put those in our cost estimate. Perhaps we should, because there is actually, some good statistical data on launch vehicles, and every so often, one's maybe not going to make it. But we're cognizant of it, and we look at it in our planning. What is what is our answer to like a failed launch? And so, and usually what the answer is, well, you just kind of slip that mission to the next opportunity, rather than having another launch vehicle standing by to make up for it.
Joe, do you have anything to add to that as far as contingency planning?
Yeah, I'm just looking a little bit at our report that we did for the Group 1 again. And one of the things that we did do is we built in what we call block redundancy. So we had a couple of different stages that you would use if you went all the way to Mars. We had the ability to use those also in abort scenarios, so that, let's say we got to Mars and there was a problem and we didn't want to stay, we had the ability to use those to get home more rapidly and that sort of thing. So it was something where we took that into account, and that would have been something that was included just by definition in the budgets that we showed you earlier. So that was part of the overall architecture of the Group 1 spacecraft.
And did you say at the top of the Hangout that this sort of presupposes, this chart we showed earlier showed that you're spending less than the ISS equivalent budget per year, adjusted for inflation, which went anywhere from $4 billion to $7 billion through 2045. Are you sort of, what role is the ISS going to play in this? Does that money have to become free from the ISS before we can spend it on this? Or is this another pot of money? Are you depending, for example, on the fact that the ISS is going to be decommissioned and run by private company and not NASA? Is that how you're going forward with the thinking?
We've showed it as something that, what's on the books right now is a gradual phase out. And, there was a proposal this year in the budget to stop it in 2025, which we don't think is, I don't know what's going to happen, but, there's different people with different dates. But what we, I think, assumed was a phase out by about 2028. And so that budget is going down in terms of the NASA spending on it. And what you saw on that sand chart reflected that.
Yeah, okay. Okay, I want to remind everybody you are watching a Future in Space Hangout sponsored by the American Astronautical Society and endorsed by the American Astronomical Society. And every week we come and we talk about aerospace and aeronautical issues in our Future in Space Hangout every other week. So I want to thank them for joining us. My guests today are John Connolly from NASA Johnson Space Center and Joe Cassady from Aerojet Rocketdyne. Both of these guys have been working on trying to get us to Mars in an affordable fashion and debunk the myths that it's going to be $1 trillion thing. I'm actually quite amazed, guys, at what you've come up with, and that this is actually something that can be done. I remember, I think it was in the 90s, I heard somebody put a price tag on going to Mars at $300 billion. And this was, I think, a number that I think somebody just said. But this is actually spread out over, what is it, 2025, 2030, over 25 years or so. We're spending much less than that, so that's pretty good. Even if you're not, I mean, let's say you're only within 20%, this is still a pretty affordable thing, isn't it?
Right.
So what's the political, okay, I'm gonna ask it, you don't have to answer it. What's the political will for this kind of thing? Is NASA, do you guys just don't think about that, or you just need to be ready when someone tells you to do something?
Oh, we think about it. Yeah. I'll jump in. I'll put my.
Yeah, you don't work for NASA, Joe. You could say.
Right, I don't work for NASA, but I've got my Explore Mars hat on, so now I'm a nonprofit guy, right?
Yes.
As I said earlier, we worry a lot about the outreach. How do we get to Capitol Hill? Every year we deliver a copy of our Mars report to every congressional office. Every single congressional office gets a copy of the Mars report. And what we're telling them is this story, that you can do this, that it is affordable. And we're seeing a lot of results from that. I really believe, there's support for this on both sides of the aisle, both houses of Congress. We don't get a lot of people. Every Congress has somebody who says, there's better things to do than space, in general. But as far as Mars goes, I think a lot of people are somewhat inspired by the idea that we could take this as a long-term goal and set the goal out to set foot on Mars in 20 or so years. And there's been some real tangible progress. I mean, you look at NASA's budget over the last few years. It's not decreasing. It's not flat. It's actually been increasing. That is
and quite
Congress
encouraging.
Usually takes what the president proposes and gives them a little more.
Yeah, I know. It has been a nice surprise. It has been. Okay, yeah. Professor Masters, Karen Masters from Haverford College, is asking some questions from her students. They're watching this Hangout from their classroom, I think. And one of the questions is, how much more than the early cost projections do crewed space missions cost? How much more than the early cost projections do most crewed?
Sort of a rule of thumb, huh?
Yeah. What do they generally cost?
Boy, good question.
So you'd have to go back to some missions that we actually did cost estimates for and then actually flew. So there's some good history on Space Shuttle, what we originally thought its cost per flight would be, and its actual cost per flight ended up being quite a bit more than that. I'm sure there's some estimates on what we thought the space station would cost and what that's ending up being. And then most recently, Orion and any of the commercial crew vehicles. I don't have those numbers on top of my head, but it's almost guaranteed that whatever we estimated them for, the actual cost is higher once we actually did it.
I know.
And again, that's just the unknowns in our business. We're really pushing the envelope here, and whenever you're dealing with equipment that's never been designed before, never been flown before, it's very hard to use cost estimating tools that use analogies to find the right answer. So we do the best we can, but we prepare ourselves for the fact that it might likely cost more than that.
Right. I mean, even I'm just, even if this is an order of magnitude estimate, the main point here is that this isn't infinitely expensive. As Harley said at the top, this is actually something that can be done. We're getting a handle on what they can cost within some error bars, and I think this at least is telling the story that it's not going to break the bank, especially if we work together as a planet instead of as a country to get this done.
Right.
She's asking another question. Does the development of 3D printers make missions like this more feasible than they used to be? Because there's this place called Made in Space. They print up things on the International Space Station, and they're making parts. Is there a role to play, and does that go into your cost estimate?
I got a real good specific Aerojet Rocketdyne example on that one. We're applying additive, we call it additive manufacturing. Same thing, 3D printing.
Mm-hmm.
We're 3D printing major pieces of our rocket engines now. We're going to use on SLS, we're going to use the same rocket engine that was used on the space shuttle as the main engine on the orbiter. We're going to get the cost on that down by a large percentage, I'll say. I probably shouldn't say the exact number because somebody at NASA will write it down and I'll be on the hook to hit that number. But we have made major strides in using additive manufacturing. Rocket engines are, if you ever look at one up close, you see a lot of little pieces and wires and tubes sticking out. And one of the things we can do with additive is we can, in one printing, take up a lot of what would have been maybe 50 or 100 separate parts that had to be swaged or brazed together, all by hand. And we can do that as a printed part. That saves a tremendous amount of cost in terms of the manufacturing time as well as schedule. And that's what brings the cost of those engines down. So that'll contribute. You heard John say earlier, propulsion is the big cost. So by getting the cost of those things down, and also, we're looking at better propulsion that costs us less in terms of the propellant we have to raise up there into space.
Exactly.
So additive manufacturing and those advanced propulsion technologies like solar electric propulsion are two big things we can do to help on the propulsion cost that John talked about.
Okay, we have just a couple more minutes. I want to get to these last few questions. Question from a student. I think his name is Sam. How heavily dependent is the plan that you've come up with on new technology development? For example, for radiation shielding. So we all know JWST. New technologies, blah blah blah. But how dependent are you on knowing about these technologies?
So I think it varies. We talked about 3 architectures at the very beginning, and Joe mentioned that one of the architectures was very low technology, current technology, and so that didn't depend very much on big technology advances. Whereas some of the ones as you go towards permanent colonization of Mars depended very heavily on things like in situ resource utilization and others. In terms of radiation protection, I think we pretty much have that. We know that there's a certain amount of mass and the right kinds of mass that you have to add to a spacecraft and design it the right way to get the radiation levels down to a reasonable amount. And there's just certain types of radiation that are very hard to shield against, regardless of what you do. In fact, certain kinds, the more shielding you add, the worse you make the situation because of secondaries. And so I think there's there's a broad spectrum of how you apply new technologies to the mission. And as you apply new technologies, yeah, it's true. Usually the overall cost comes down a little bit because it gets a little lighter and everything's about propulsion and moving mass around. But you have to absorb the cost of that technology too.
Okay, I'm going to ask the last question because we're out of time. This is a good one to end it with. What are you guys' opinion? How real? This is from one of the students in the class. How realistic do you guys think the Martian movie was? Give us your opinion. Start with you, Joe.
Okay, so you heard a couple of comments I made earlier, probably about the spaceship and the types of things. Some of that was a little bit more what I'd call second or third generational.
Yeah.
But in terms of the crew on the surface, the windstorm,
everybody has a problem with that. Everybody has a problem with that.
Yeah, the air pressure just isn't that strong. It's 1/100th of our pressure. But I liked a lot of the stuff. I'm an old satellite propulsion guy, so hydrazine. He got the hydrazine out of the engines that he was using that to generate. A lot of that was very well done. Andy Weir's. I just read Artemis.
I'm reading it now. Yeah.
Yeah. So he does a lot of good research, and he basically his stuff is pretty good.
John, what did you think? Was it very realistic?
Parts of it were. I think maybe the most realistic thing was the series of challenges that you'll have during a Mars mission that you constantly have to overcome. And you're right. The scene at the beginning, Andy wrote that because he needed some big event like that to precipitate one person being left on the surface with an antenna sticking in them.
Right.
But generally, as he was going through writing that book, he was writing it as a series of blogs, and we were keeping track of this, of course. And he did a lot of good engineering as he went through that, and so we gave him a few hints along the way. You know, he was always getting inputs from people, and then one day all his blogs ended up in an ebook, and like about an hour later, he had sold the rights of the book to Hollywood. And so he's a good engineer, so he does his homework.
My favorite scene was when he went, I think it was, I don't know if it was Sojourner or Pathfinder, but he goes to one of the old, and he uses the camera to communicate. That was my favorite scene. I love seeing those old rovers that, you know, just, and the fact that he got it fired up, maybe that's a little unrealistic, but still, that was a great idea. Okay, we will stop there. I want to thank you guys so much for taking time out. You guys are awesome. You guys are great for coming on these Hangouts, so I do appreciate it. My guests today were Dr. John Connolly and Joe Cassady. John is from NASA's Johnson Space Center. I keep wanting to call it Space Flight Center. And Joe Cassady is from Aerojet Rocketdyne. These guys are working on trying to figure out how much it's going to cost to get us to Mars, really, and can we do this? And the answer is, yeah, it's a lot cheaper than we thought if you take into account a lot of these things. And I think their projections are realistic. What are you showing there?
It's my little sticker, and it says 2033, we can do this.
Okay, we can do this. I want one of those. Yeah, so it can happen. Obviously, we all know the realities of getting things done with political will, all of that, but we all want to go to Mars, and it's going to happen. And we just got to, but at least these guys are solving the biggest problem, which is how are we going to pay for it and how much is it really going to cost. And they're laying the groundwork for getting us there to Mars. So thank you guys very much for your work. I appreciate it. Next week, folks, we're going to have Telescope Talk on Wednesday, where we've got Jason Major will be one of our guests. We're going to be talking with him and talking about imaging and processing and things like that of astronomical images. I don't have a Astro Coffee Hangout topic planned from Carol yet, but the following Astro Coffee Hangout is going to be awesome. We've got the author of a paper that I think came out in AppJ talking about whether or not climate change can be a great filter or a solution or an answer to Fermi's paradox of why we haven't seen anybody. It's an interesting paper. I'm doing a Space Fan News on it right now, and that'll be toward the end of the month. So you want to make sure you check that out. Okay, folks, I want to thank all of you guys for watching. I want to thank the AASs for sponsoring. Thank you guys for the great questions, and keep them coming. Hopefully, I'll see you guys next Wednesday and Thursday with more Telescope Talks. Thank you all so much for watching. And as always, keep looking up.